Yeah, we're back at it here. We got 2 more weeks, or like a week and a half, right? We're gonna finish up a couple things. The thing I want to finish up from my side of the world is, I know Catherine spent some time doing regression with factors with you guys, which I really appreciate. I think it's a cool thing. And just giving you guys a high level overview of that. I'm gonna spend this week giving you guys a high level overview of kind of how we do model selection, how we think of that. Now, I'm not going to get to everything in that world. Like what we're going to talk about this week is actually what is the hardest problem in statistics and machine learning. Like it is truly the hardest problem because nobody knows how to do it right. Like there are things we know how to do, which is add and subtract, multiply and divide. Everything else is an opinion. All right. And I'm going to show you the methods we know and we think work, and then show you some things that could work, maybe kind of sort of in certain scenarios, and then show you some ideas and then say, look, we're going to get to some of this stuff in 451 and some of this other stuff we really don't know how to solve. You guys are starting to hit the boundary of the methods and the things we actually know how to do well, which is, I know, kind of a different take than what you guys are used to in a lot of classes, right? You guys are used to people standing up and saying, no, we know how to do this. This is sound. This is factual. One, I think you guys understand I'm not arrogant enough and Catherine's not arrogant enough to ever say that to you. The second thing you'll figure out is stats is a very new field relative to what you guys are used to talking about. And so when I tell you something is factual, it's mathematically provable, but that doesn't mean it applies everywhere. So some of the stuff we're going to talk about this week has this like, well, kind of, sort of, we could do this feel, which is, I know, different for you guys, but I want you to know that we'll talk through it. I'll show you some examples and we'll do that as well. And then next week, we're going to get into some data visualization tools. I think Catherine, Tableau, right? Going to talk through some Tableau ideas. I know Catherine may bring up some Power BI stuff. We're not going to get deep into Power BI, but maybe just talk about its existence and who's using it. And then that'll kind of tie up the class there. So before we get going there, any questions from anybody? All right, I'm going to share my screen.
Brad, while you're doing that, I'll just mention too, we've got, I know you guys turned in assignment 7 right before the break, so we'll get those grades posted this week. Assignment 8 we'll kind of grade as we go. The, you know, what will I be when I grow, what do I want to be when I grow up assignment, like that one we'll kind of grade throughout. But you guys, I mean, again, that should be an easy A, so we'll have those graded by the end of the semester. And then we'll get assignment 9, the last assignment, posted by Thursday this week, so you can get it turned in by the last day of classes next week. And we'll also have some details on the final exam probably next Monday to give you an idea, but it'll be like a take-home exam. We'll give you at least a week to get that completed. So you should be in good shape there.
Yeah, the other thing I want to tell you guys, and this is something I want to be, you know, real upfront with you about, is just how proud I am of you and how you guys have pushed yourselves. Like, seriously, I don't want to get all, you know, all emotional on you guys before the end of the semester here. That's not how this works, you know, all Thanksgiving. But it's one of those things. I really am proud of you. You guys had some curveballs thrown at you this semester, and you guys have adapted and you've adjusted, and you've really shown your ability to, and I hate this word in the middle of at the end of the pandemic here, pivot. But the other thing you've shown is your ability to adapt and adjust and overcome. And, you know, don't think we're not aware of that. Don't think we haven't seen that. Don't think it's not something we're not tracking. So just understand how proud we are of you. Just understand, we know you guys don't have to take this class. We understand it's a minor. We understand it's those things, but how much you guys have pushed yourself in this class, and just understand how thrilled we are with how you've done. And so to reward that in a certain way, this will be the first time I've ever given extra credit in a class in my life. I don't give extra credit. I don't believe in it, except in situations like what we've done here. There's this thing happening, and you guys have heard about Data Robot, right? If you guys haven't heard about Data Robot, guess what? You're gonna have an opportunity to hear about Data Robot. Data Robot is having an open house at the Alumni Center. It is on Wednesday from 10 a.m. to 6 p.m. It is not mandatory. I am not saying you must go. I am not saying you have to go. I am saying I would love for you to go. I'm saying if you're interested in doing data analytics for a living, you should go hear what this group is about. There's some really cool people going to be there. They have some really cool ideas. They have some really cool ideas on how to use AI and machine learning in this stuff. We're going to talk about them in 451. You guys are actually going to write a position paper on them in 451. If you guys are going to come hang out with me in 451. They have presentations at 2, 3, and 4, but you guys can go over it anytime between 10 and 6. This is worth 10 extra credit points. So 10 points on a homework basically is what I want you to think of it as, okay? I think that's what Catherine and I agreed on there. Yeah.
Yeah, so that's for BUDA 450. I'm going to have to reach out to Dr. Shop and see if he's willing to do the same for the accounting 493C students. But for BUDA 450, it would be 10 extra credit points. I know that the CCD will be there with like the swipe machine, so I'll just get the list from them of who all attended to provide the extra credit. But also Brad and I'll probably head over there, you know, grab a bite to eat after class on Wednesday and then head over there in the afternoon. So you know, we see your names, but we don't know all the faces. So be sure to like stop by and introduce yourselves to us if you see us around. The other thing I'll mention, I mean, it's kind of like a career fair from the standpoint, like you can definitely talk to them about career opportunities, but we know not all of you are in a position to be looking for an internship or a full-time job, and that's absolutely fine. But it's a lot more informal. They have representatives from their organization in a variety of different roles. They just want to kind of talk to you and get to know you and vice versa. So it's probably not like an event you've been to in the past, from what Brad and I experienced with a similar event over the summer. And they're a startup culture, so business casual attire is absolutely appropriate for this. You do not have to be in a full suit. They, you know, they tend to dress more business casual themselves, so don't feel like you've got to put on a suit just to go over there for an hour or two.
And this is something you can swing by in between classes, okay? Stop in, see what they're about. This is one of those things for you guys. This is one of those companies that, and I was joking, I'm not really joking. I told you guys one of the reasons I came back to West Virginia, right? The other reason I came back was because I've got to work with companies like this at my other stops. These are the type of companies, them, Leidos, Nobilis, you know, MITRE, Bravo. I can go down the list of the companies that I want to see here and I want to see operating and I want to see doing the cool things that they're doing other places, except I want them doing it here. You guys chose to come to West Virginia for a reason. There's a myriad of reasons you guys chose to come here. All right. I don't want you to have to leave to find a job. Companies like this coming here, that's a big deal to me because they're doing really cool stuff, but they're doing it nationally out of Morgantown. All right. So go check out what they're doing. Go see what it's about. That's the only thing I'll
passengers based on federal and TSA guidelines.
Swipe in for me. And Catherine will send out some information on what we're actually going to count for the extra credit and all that stuff. But again, if it's one of those things where the swipe doesn't work, take a picture of yourself there or something and send it to us and we'll figure out how to make it count. Okay. Everybody good with that before we get into this other stuff? Any questions? Like I said, I'm not a big extra credit person. This is also my reward for you guys pushing yourself this semester. We've asked you to do some things nobody who's ever taken BUDA 450 has done before. And as the reward for that, you guys pushing yourself, I don't want to penalize you. I don't want to do those type of things, okay? I want you guys have done everything in the world we've asked, and I'm super proud of that. And I'm super happy about that. So as your reward, rather than penalize your grade, give you an opportunity to do something like this, all right? Y'all good with that? Remember, network, shake hands, say hello, fist bumps if you're pandemic concerns, like all that stuff, all right? Go say hi. These are people, they're very nice, I promise you. All right, they're very nice. And they want to know about you and what you're interested in. So don't be scared to talk about yourself. The other thing, bring a resume. All right, I'm going to say it louder this time so you can hear me. Bring a resume. Don't be like, oh, I can email. Bring a paper one and then have one ready to email them immediately. Okay. I need thumbs up on this one, guys. This is networking 101. Need some thumbs up on that one. Y'all with me on that? All right. All right. All right. Let me close this out. Enough career 101 here. So we posted some notes yesterday on model and variable selection. And I'll start off by saying what I said a second ago again. This is the hardest problem in statistics and machine learning by far. And let's go ahead and talk about what model and variable selection are. Model and variable selection are about, and everybody can see my screen, right? Got it. Appreciate y'all. Now, model and variable selection by far is the hardest problem, because what I'm asking you to do right now is what we call model comparison. I'm asking you to say, look, I'm going to fit two models, and I'm just going to write a model up here. Let's say I have a response Y, and I'm going to fit it against X1 plus X2 plus X3. And I want to say, is it better than Y against X1 plus X2 plus X3 plus X4? And what I'm asking, let's call this thing M1. Let's call this thing M2. What I'm asking is, how do we say M1 is better than M2 or M2 is better than M1? And if I make it even more complex, when I'm asking this question, I'm asking, are variables X4 and X5 important in my model? Is this something that is helpful in my prediction or in my inference? Now, there's a lot of ways we can do this stuff. There's a lot of ways to think about this. But I want you to think back. I want you to think way back to what we've talked about. I want you to think way back to how we've done stuff in this course, okay? Now I want you to think about this. What we've done is we've said, I want to do transformations. I want to do all these different things. And I want to see if it makes my model better. I want to see if it meets diagnostics. I want to see if it meets interpretation. But at some point, somebody's going to ask you, which model is better? How do you know that's the best? And that's where you got to say, well, see what happens is, that's when you got to step up and say, well, because I did this, this, and this, and that's what it says. That's your last point you drive home. You know how to interpret. You know how to make sure your assumptions are met. Now what we've got to do is say, you know what, I fit a bunch of models and that's the best. Y'all with me on that? That's what we're doing here. All right. So now, throughout this course, we've discussed methods to build and fit models that meet a certain set of assumptions. But as we move forward, how do we select a model out of a group of possible candidate models becomes extremely important. We'll start off by discussing some metrics that are possible to use, and then the computational ways to begin to select models. Our focus will be on variable selection for discovery more so than theoretical models. Now, here's what I mean by that statement. I'm going to let the data tell me what variables are important. There is this new concept. All right. I just published a paper on it. There's some other papers that have come out on it, where what we try and do is we try and bring theory in from different fields. Okay. And combine it with data to create what we call informed approaches. So I know everybody's COVID exhausted. I know I am, because that's Catherine and I, especially, that has been our lives data wise. All right. You guys, I know, have been worn out by it because of everything you've had to deal with school wise. But think about this for a second. If I can take biostatistics and public health models and infectious disease models and bring them into data to inform predictions on where COVID outbreaks are going to occur, I can inform restrictions or testing or vaccination sites a lot better, right? When we talk about theoretical models, that's what we're talking about. When we talk about it in business, what we're talking about is supply chain models, econometric models, marketing models, financial models, all these different models where we can bring the theory in from these fields and use it to inform models we build off data. From our perspective right now, when I'm teaching you the basics, I don't care about that. That's a much more advanced concept. For right now, what I want to do is just show you the mechanisms that are there, okay? Now, the other thing you need to understand, this is where much of the statistical and machine learning research is right now, all right? And the reason is because this is the hardest problem going, all right? By far, this is the hardest problem going. How do we select models? Now, there are really two ways to evaluate models. One uses methods that require a singular fit. We fit one model and then we evaluate it. The second is to use computationally intense methods that evaluate out of sample predictions. Basically, think of this as what we call a test train. So the way I want you to think of this methodology, okay, and I'm not going to get real deep into this. We'll save this for 451. But the idea, how many of you guys have ever taken a practice test? gonna say it's after Thanksgiving. Ain't nothing changed yet. How many of you guys have ever taken a practice test? Thumbs up, thumbs down. All right, we've taken some practice tests. Good. The idea, does your real test look like your practice test? Should look similar, but not exact, right? So the idea is that what we're going to do is we're going to fit a model like it's a practice test. And then we're going to evaluate it on some test data it hasn't seen yet, just like we do when we give you guys a test. All right. That's what I mean by an out of sample prediction. Now, the trade-off in these scenarios is, all right, what we're looking for from a model. If a model predicts well, then we want to use out of sample prediction, which to me is what we look for a lot of times in business. How well is it going to forecast? How well is it going to predict outside? All right. Now, the other thing we can do, all right, is we can say, what happens if it's just a singular fit? Well, what you're going to see as you move forward is these computationally intense methods waste a lot of time. They waste a lot of resources. And as you move out into the business world, you're going to be running on what we call servers, right? You guys are going to be running on AWS. You guys are going to be running on Azure. You guys are going to be running on whatever, right? And what we're looking at and what we're thinking about there, all right? And what we're looking at and what we're thinking about there, all right, is cost. So when we run these computationally intense methods, it's not going to work so well. Like I said, we're going to get into that computationally intense stuff in 451, but I'm bringing it up here just so you know it's out there. All right. Now, there's also other tools out there like parallel computing, and we'll talk about that in a different class. Now, one of the things we've talked about is R squared. Let's talk about R squared one more time. Somebody remind me, what is R squared? Abby, you have a question, or is your hand still up from just when we were talking a second ago? Ah, got it. No, you're good. You're good. Just double checking. So who remembers what R squared is?
It's the measure of the correlation.
Correlation between what? That's good. That's a good start. Correlation between what? There's two ways. We think of it as the correlation between the response and the fitted values of the model, right? That's one of the ways we talk about it. That's good. The other way we talk about R squared, right? It's the percentage, what? It's the percentage of variation of the response explained by the predictors. So what we can always do is we can say, look, this is just the percent of the response, percent of variation in the response explained by the predictors. And that's great, except R squared is extremely flawed. What it says is the more predictors I add, the higher the R squared. Doesn't matter if they're associated with the response or not. And I'll prove that to you later. So what we have, all right, what we have is all these different methods. So what we're going to talk about now are the metrics themselves. What numbers do we use to evaluate a model? So the way I want you to think about this is we're going to talk about metrics, and then we're going to talk about methods for evaluating model. All right, what's the difference? The metric is the actual number we're going to use to compare. Methods are what's the systematic way we're going to go about doing model comparisons. You guys good with that concept? So the first one's R squared. It's the percentage of variation explained. It's way flawed, and you should stay away from it. Forget it exists until after you've picked a model. Y'all good with that? Notice I don't even write it down. But then there's this thing called adjusted R squared. All right. And what it is it's this calculation. All right. And all it is what we call a degrees of freedom adjusted R squared. R squared by itself is flawed because the more predictors we add, the higher it goes, no matter what. You could add just random noise to your model and your R squared would increase. You could add a predictor that has no association with your response and your R squared would always go up, which means we would always have a better R squared, and that's great, right? No. We know it, models get harder to interpret the more predictors that come into them. You guys agree with me there? You've got more coefficients to interpret. That's problematic. So as the number of predictors goes up, models get more complex. So there's a balance point we want to hit. We only want to add important predictors. You guys agree with me there? Think back to our added variable plots. Think back to all of those things. We only want to put a predictor in if it matters. Everybody agree with that statement? So what we're going to do here is we're going to adjust it. Adjusted R squared says P is my number of predictors, N is my number of observations. So a predictor, all right, we're going to adjust R squared with this ratio. And what that ratio does is it considers the number of predictors that went in with the number of observations. So if you're just throwing predictors in because you're like, whatever, it's going to really deflate your adjusted R squared. All right. So adjusted R squared, we still want a big value, but it doesn't have that pretty interpretation. It's just a metric we use to select. All right. Now, the information criterion. All right. The information criterion, you're going to hear me call these AIC and BIC. All right. And we'll talk about those here in 1 second. The idea with information criterion is to take into account a single model fit. We're going to call that model N, and the complexity of the model. We know as the number of predictors increase, all right? All right, this is a fact. As the number of predictors increase, the residual sum of squares of the model will always decrease. So here's M1, here's M2. The residual sum of squares associated with M2 is always smaller than the residual sum of squares associated with M1. That is a fact. All right. Because of that fact, that goes back to that R squared point. R squared of M2 will always be bigger than the R squared of M1. You'd always choose M2 if you were using R squared. I don't even have to tell you. I don't even have to tell you if X4 and X5 matter. You'd always do that. So what we use is we use these trade-offs between the number of predictors, all right, and how good the model actually fits. To add X4 and X5, what we want to do is say X4 and X5 have to bring so much of a decrease in the residual sum of squares, right? What's the residual sum of squares? It's how good does my model fit? What's the difference between my line and the data, right? That's the residual sum of squares. So what we want to do is when we look at this, we want to say, hey, how much decrease does that bring? Is it a big enough decrease in the residual sum of squares? All right. So here's what we're going to get. All right. Here's what we're going to get. We're going to use what we call the Akake information criterion. And for short, we're just going to call it AIC. All right. Which what we're going to say is for a model M. All right. For a model M, we're going to do this calculation where N is the number of observations. The residual sum of squares is the residual sum of squares for a given model. And P is just the number of predictors. Okay. Now, I should have moved this beyond because we're going to talk about ANOVA a little bit later. All right. But the idea here is this is my information criterion. Now, any model we fit has an AIC as long as it has a residual sum of squares and we know the number of predictors and observations. Lowest AIC wins. Hear me again. The lowest AIC wins. You guys good with that idea? R squared and adjusted R squared, bigger numbers. AIC, lowest AIC wins. We also have this thing called BIC, which is the Bayesian information criterion. Now I want you to look at the difference. First term is the same on both of these. Second term is the difference. All right. It's just a different weighting on how we treat the number of predictors. All right. BIC, again, smaller values preferred. We're going to take two models. We're going to calculate the BIC, and the better model is going to have the smaller BIC. The next thing we're going to do is we're going to have cross-validation. All right, cross-validation is something we're going to cover heavily in 451. I've got a couple paragraphs here for you. I'm not going to spend a lot of time on those. All right. We've got R squared, adjusted R squared, AIC, and BIC. All those are numbers. You just calculate them. You take them, you throw in a model, and it works. They're a metric. Okay. And we're going to talk about those metrics as we go through our methods. Cross-validation, it's a method and a metric at the same time. What we're doing is we're looking at out-of-sample residual sum of squares. We're saving that for 451. That's just for your knowledge for later. I'm not going to evaluate you on that. What I do want to start talking about today, though, is ANOVA. We're going to spend a little bit of time on ANOVA this week. How many of you guys have talked about ANOVA in any of your classes? Nobody's talked about analysis of variance before. All right, Sarah, Kendra, help me out here. What's ANOVA about?
Doesn't it just kind of help you to like interpret the data when there's a lot of it? That's kind of what we used it for.
It can. It
Okay,
can.
yeah.
Kendra, anything to add there?
That's basically all I was going to say too, the analysis of the variance.
There it is. Okay. And here's what I want you to think about now. A lot of times this is taught in a different way than what I'm going to teach you. Okay. This is one of those ways we're going to use it to trick a model. All right. A lot of the time you've been taught how to test hypotheses in that we're going to test that a parameter is equal. Think about our regression test, right? Where we say the slope is equal to 0 or the slope is not equal to 0, right? When we're looking at regression output. All right. Where we do this test and everything works out great. But what we actually want to do in regression is we want to compare two models. All right. We want to use what's called an F test. You guys are used to T tests. What I want to talk about today is an F test. F tests are this weird thing. All right. But what it's going to allow me to do is test a model that looks like this. Imagine I have model 1, which has predictor X1 and regression coefficient beta 1. And model 2, which has predictor X1 beta 1 and adds predictor X2 and regression coefficient beta 2. Now, if I'm asking you to compare M1 and M2, what am I actually asking you to compare? If I'm asking you which model's better, M1 or M2, what am I actually asking you? Think about it for a second. If I'm asking you, is M1 better than M2? Or is M2 better than M1? What am I asking you?
Is it which one provides like the most information?
Okay, great. Which one provides the most information? So let's start with that statement, and then let's take it one step further. What's the difference between M1 and M2 right now? What's in M2 that's not in M1? Would it just be X2 beta 2? X1 beta 1 is in M1, right? X1 beta 1 is in M2. Does everybody agree with me there? X2 beta 2 is not in M1, but is in M2. Would you guys agree with me there? The question becomes, if I'm asking you to tell me, is M1 better than M2 or M2 better than M1? I'm asking you, does this provide any useful information? Would you guys agree with that? That's my question. When we start talking about this, guys, remember I tell you, critical thinking is what this is about, right? What we have to do is we've got to take the mathematical down to the fundamental question we're actually asking. Does X2 beta 2 actually belong in this model? All right. What does it add? All right. Now, I want to talk about two concepts real quick. I want to talk about the idea of a submodel. A submodel says I can find every variable of one model in the other model. M1 is a submodel of M2. because I can find every variable in M1 in M2. Would you agree with me? X1 beta 1 is in M1. Every variable in M1 is also in M2. Would you agree with that statement? Every variable in model 1, M1, is also in model 2, M2. Do you guys agree with that statement? What I'm saying is X1 beta 1 is in model 1, and X1 beta 1 is also in model 2. Everybody agrees with that, right? That is the definition of a submodel. We say model 1 is a submodel of model 2. It means it's a simpler model. Okay? M2 is not a submodel of model 1. Does that make sense? M1 is a submodel of model 2. Let's come back up here. Let's look at the top again. In this case, mod 3, mod 4. Okay. Is model 3 a submodel of model 4, or is model 4 a submodel of model 3? Every predictor, definition, right? Every predictor that is in the submodel must be found in the bigger model, right? Is X1 in model 3 and model 4? Yes. Is X2 in model 3 and model 4? Yes. Is X3 in model 3 and model 4? Yes. Is X4 in model 3 and model 4? No, it's just in model 4. Every variable in model 3 can also be found in model 4. Do you guys agree with that statement? Every predictor variable, every X variable that is found in model 3 can also be found in model 4. Do you guys agree with that? That means model 3 is a submodel of model 4. Now, let me change one thing on you. X6. Is model 3 still a submodel of model 4? Austin, help me out. Why?
It's because there's a variable that's not in model 4.
X6 is in model 3, but not in model 4, right? Now, this submodel idea is really important because here's why. All right, this submodel idea is really important, and here's why. It's because we've always talked about, right? We've always talked about this idea that the null hypothesis is always the simplest answer, right? The null hypothesis always has the equal sign in it. Now, here's what I want you to understand. If X2 beta 2 in this model doesn't matter, these two models are the same. Would you guys agree with me? If this beta 2 is 0, these two models are the same. Would everybody agree with that statement? That just means it's X1 beta 1 plus X2 times 0. That disappears, right? That would just be X1 beta 1, X1 beta 1, right? Those two things are the same. Would you guys agree with me? And we've already said M1 is a submodel of M2. Since it's a submodel, we say it's the simpler model. So say M1 is the simple model, M2 is the complex model. M1's the small model, M2's the big model. All right. The null hypothesis in this is the small model is better. Hear me out when I say this. Hear me when I say this. The null hypothesis is the small model is better. I'm going to say it again. The null hypothesis is the small model is better. The alternative hypothesis, the big model is better. It's real simple. If we're comparing two models, they have to be submodels using ANOVA, okay? We know what submodels mean. Means we got to find every variable in one of the models that's in the other. The null hypothesis is the small model is better. The alternative hypothesis is the big model is better. You guys good with that idea? All right. Now, there's a bunch of math reasons this works. But it basically comes down to if one is a submodel of the other, the submodel always has a smaller residual sum of squares. It has to. Theoretically has to. Computationally will always. All right. Now, because of that, we can use what's called an F-test. We'll get a p-value back. And when we get that p-value back, what we'll be able to do is run a hypothesis test. If we reject the null hypothesis, what we do, we pick the big model. If we fail to reject the null hypothesis, we pick the small model. That's all it comes down to. So why am I calling this a metric? Why is ANOVA a metric? Because what we're going to do is we're going to use a p-value to pick between models. All right, we're going to use a p-value to pick between models. Now, let me show you how this works. Let me show you the first thing, and this will be, we may get through all this today. I will get through this one example. All right. The overall F-test. This is something you've been looking at all semester, but you ain't seen. Now, how you been looking at something all semester, but you ain't seen? Because we haven't talked about it. You've been looking at it. You've been glancing over it. I've been telling you, ignore it, ignore it, ignore it. Today's the day we stop ignoring it. You've been running this ANOVA all semester. You just haven't seen it yet. All right. We're going to look at the simplest case of an ANOVA. The simplest case of an ANOVA is the null hypothesis. The simple model is the intercept-only model. Okay. The intercept-only model says the expected value of y given x is just the mean. We're not going to use a predictor. We're just going to predict the mean every time. All right. That is the dumbest is a bad word, but it's what I can come up with today. That is the silliest. I'll talk to it like I'm talking to my 6-year-old. That is the silliest thing we can do. The most uninformed thing we can do. We'll go with that. And then we're going to compare it to adding a single predictor. Okay. Now, here's all the math that it comes up with, and this is great. But what I want to do is I want to run this one time and show you where this comparison is. So I'm going to load up the ALR4 library. We're going to attach the UN11 data set, and I'm going to fit this model. Okay. Now you see it running down here. We're going to look at the summary. Now, we fit a model, life expectancy of females against log PPGDP. Great. We fit this model a bunch. I'm not going to go through the interpretation. Here's what I want you to look at. There's this F statistic way down here at the bottom. This F statistic way down here at the bottom. This is that overall ANOVA that is testing this. This F statistic p-value, it says the null hypothesis is that you should only use the mean of y. You shouldn't use any predictors. The alternative hypothesis is you should use the model you fit. And here's the p-value. Basically, what the overall F test is asking is the model you fit better than doing nothing? It's the single model comparison. If you can't beat this benchmark, you shouldn't be fitting regression. It's saying, does a single predictor work better than anything? If the answer here is no, you should stop the analysis right now and be like, look, we can't do any better than the mean. This is your first statistic. This is your first model comparison. This p-value right here, we always say p-values less than 0.05. We either reject or fail to reject. P-value small, we reject the null hypothesis. The null hypothesis in the overall F-test is that we should use a model with no predictors. We reject the null hypothesis. So we're going to select the more complex model, which is what? The model with regression coefficients, the model we fit, okay? So that's the overall. Now, there's another piece of code right here that we can run in ANOVA, and you're going to see this. I want you to notice this F statistic of 29 or 291.1. This is what we call our ANOVA table, okay? You'll see that 291.1 show up right here. all of this stuff looks great. And this is how we publish papers. And this is how we do all this stuff. For you guys as practitioners, for you guys who need to do model comparisons and then go interpret, you don't care. Like, that's just me being straight up blunt with you. You don't care. I put it all in here for you because at some point you might. At some point you may want that information. But for what we're doing today, for what we're doing in this class, you don't care. Because what we care about that p-value. And we care about understanding what that p-value means. What's that p-value mean? That p-value is asking you about this question right here. Should I be using predictors or should I not be using predictors? P-value says p-value is less than 2 times 10 to the negative 16. That's less than 0.05. Since my p-value is less than 0.05, I'm using 0.05 because that's what we've been using in this class, right? We reject the null hypothesis. By rejecting the null hypothesis, what we're saying is we're selecting the big model, which in this case is saying log PPGDP. Now, what we're going to do on Wednesday is we're going to take this idea and scale it to say this overall F test is great. That's like testing one sample means. I don't care what one sample means are. I want to compare different models. I want to put a bunch of predictors in here and see what they do. All right, let's do that. Let's do that. So on Wednesday, what we're going to do is we're going to start comparing models with multiple predictors. And the same idea is going to hold. Look at this. This is still a submodel. The null model, right? Since this is an intercept-only model, I can find it in the alternative model. This is a submodel of the alternative model. Small model, big model. Small model only has an intercept. Big model has a predictor in it, right? I can use ANOVA to make the comparison. So all we're going to do on Wednesday is say fit 2 models. Use this command right here to compare them. All right. And I'll show you a couple tricks that go with it. But 5 minutes ain't long enough to do that. So I'm gonna give you guys 5 minutes back for all the times we've gone over this year. Again, Wednesday, remember, Data Robots in town. Love to see you there. There's extra credit. We'll send out an email detailing how to get that. And if you need anything between now and then, yell at us. But if not, have a great week. Stay safe, stay healthy, and we'll talk to you then.